Now, firstly, about the assignment and the doubts that you have from it, I will keep a separate doubt session in the next lecture. So the first half of the third lecture will be for discussion of doubts and difficulties in all problems up to that point. However, we will also be discussing a number of revision kind of problems with spherical mirrors today, and hopefully with those problems you will have enough means and method to solve the homework assignment problems yourself. You can always keep sharing your individual doubts, whether they are from the module or HC Verma, with me over WhatsApp, as some of you are already doing, and I will give you hints that should help you in solving those. However, for some of the tricky problems and clearing out things completely, I will keep a separate doubts section for discussion of those full solutions of some of the questions, and that will be in the next lecture, the first half of it. So let's say about 60 to 90 minutes of the next lecture will be devoted to doubts up to that point. Now, you would have also seen that in the assignment I gave you, particularly from HC Verma, there were some questions related to refraction, which I have not taught as yet. But the reason I gave it is because the application of refraction there is very simple. It is just one single formula of real depth, apparent depth, which I was telling you about last time. So in case you haven't worked out those problems, it doesn't really matter. After today's lecture, you will not have any difficulty. Okay. So let's get underway. Okay. So we saw the important thing about reflection at a spherical mirror last time, okay. And to that end, we saw that as far as spherical mirrors are concerned, for point objects, the formula for the position of the image is given by 1 by v plus 1 by u is equal to 2 by r, where we understand that v, u and r are quantities which are with Cartesian sign. So they are according to the Cartesian, or you can say sort of algebraic sign convention. Okay, and so is r actually. R is the position of the center of mass with respect to our pole with the Cartesian sign convention substituted in this. Okay, so continuing ahead in this, we will understand a little bit more analysis today. And first of all, we will start by understanding the definition of focal position for a spherical mirror. So we'll start with the definition of what we mean by focal point f, which we generally denote as, and focal length, small f, which we generally denote in the context of a spherical mirror. Now, the very simple definition, so those who are just joining in, you can just review this part later from the recording. Okay. So anyway, we just started. So we're starting with the definition of focal position for a given spherical mirror and the concept of focal length. So to start with, what is the definition of the focal position? The focal position is the point at which an image is formed for a distant. So what we mean by distant is that the magnitude of the object distance should be tending to infinity. Okay. That kind of thing. Okay. For a very distant object. That is the simple definition. Okay. There are many other ways of expressing it also, that rays parallel to the principal axis cut through the focal point and all that. But that is secondary. Okay. Let's just understand this in context of this. So when we are talking about let's say a concave mirror. So let's say this is our principal axis and concave mirror is this one. So let's say its center of curvature is somewhere over here, and we want to find the position of the focal length. So first of all, we understand that V becomes equal to the focal position, and further to that end, F is small f, which is the focal length, is nothing but the position, okay, with sign, of course, with the algebraic sign of the focal point with respect to the pole. Always everything is with respect to the pole. So in this diagram, as you can see, this is the virtual side. So the virtual side is in fact what we are taking as positive, and the real side is what we are taking as negative. So V is equal to F when magnitude of U is tending to infinity. This becomes the concept. Okay, so applying in that formula, so therefore from the formula 1 by V plus 1 by U is equal to 2 by R, we can say that we can replace the value of V as f when we replace the value of magnitude of u as tending to infinity, or in this case with sign u is tending to minus infinity. So you can see from that very simply we will get the formula that 1 by f is equal to 2 by r, which means here that the focal length is r by 2. So for the example that I've taken above, okay, so let's say this is example 1. So if in example 1 I have a concave mirror which has a radius equal to, let's say, 60 centimeters. So then according to this formula from example 1, the focal length should be equal to minus 30 centimeters, because in example 1 I should substitute r equal to minus 60 with proper sign. Okay. So having done that, what I now understand is what this is telling me in terms of information is कि कोई भी ऐसा incident ray अगर infinity से आ रहा है, that means it is nearly parallel to the principal axis. Then after refraction, it will form a real image. So all such rays, as long as they are paraxial, of course, remember we always are talking in context of paraxial rays. Okay. So these sort of rays, like this one is incident at this point q, and after reflection is going like this. This one is incident at the point, let's say, q prime over here, okay, and that is going like this, and this is giving me an image at the position. Now since the rays are coming from infinity, so that position will become the focal position. Okay. So this over here will be 30 centimeters to the left of the pole, because I've already mentioned that the radius of curvature is 60 centimeters in length. So that's how it operates over here. That's how the ray diagram looks, and that is what the physical meaning of saying that the focal length is half of the radius. Now we'll move on to convex mirror also, and we will see over there that like the center of curvature is a virtual point in the case of convex mirror. So like that, the focal point is also a virtual point. So in the case of, so what we are also understanding here, that for a concave mirror, if u is at infinity, then a real image is obtained at the real focal position, okay, where the focal length is r by 2. So this is the understanding that we have, and as you will see later that this understanding is very important from the point of view of extended objects also later when we discuss about that today, not just uh, point objects which we are thinking of now. So it's basically like my point object, or now we are talking about object distance tending to infinity. So even a larger object will look like a point object because the object itself is at infinity. So the rays coming from that point object will tend to be parallel to the principal axis and very close to it. So here again, if you visualize those angles, angle of incidence and all that, they are all very small angles. So all those derivations that we've done of this thing, I mean all those little steps that we applied in the derivation of small angle approximation and all that, they are again valid over here when we apply that. Okay. So that is the story for concave mirrors. Now similarly, let us look at the story for convex mirrors. So we will see that for convex mirrors, next example, let us consider on this time, let's say radius equal to 100 centimeters. So what will happen here is, if this is my principal axis, so called, here I'll have to show a significant part of the virtual side also. So it is silvered from the inside, and therefore the mirror is the convex surface from outside. And let's say the center of curvature is over here, and this is of course the pole. So here what will happen is, if I have rays which are parallel to the principal axis coming from so-called infinity, then they will tend to diverge over here in such a way that, as you know, what will happen here is that my normal at the point of incidence is this line. This line is my normal over here. So this line being my normal, you can understand that as the rays reflect by application of law of reflection, and they will be forced to diverge like this over here. They will be forced to diverge like this over here, as if they are coming from this point behind. Okay, so now this here is the extended. Okay, so incident ray parallel to the principal axis after reflection, it suffers divergence such that it appears to be coming from this point. Now, since the incident ray in the first place was coming from infinity, so the point where the image is formed, this virtual image at the focal point. Why? Because the object is very distant. It's extremely distant. Okay. So, in any other parallel to the distinct principal reflected ray will also behave in much the same way. After reflection, it will suffer divergence in such a way that this is what will happen. So this, as I'm sure all of you are more or less aware from a long time back, this kind of ray diagram, this is what it pertains. So in this case, this virtual point where the image is formed, that by definition becomes the focal point. Okay. Now I can even leave it to you as an exercise in geometry to show geometrically why this length, which is the focal length over here, with proper sign and all, it will be plus, but here I'm just initially writing it as the magnitude of the length. If the magnitude of the radius of curvature is 100, then you can even show geometrically by doing the kind of calculations we have done earlier why this will become 50 centimeters, because this is 100 centimeters. But however, the way I will prove it here is by using the formula, because I've already got the formula by doing the geometrical derivation. So why I want to do the geometrical derivation again? That was a general derivation for both types of mirrors, so it's applicable here also. So 1 by V plus 1 by U is equal to 2 by R. Now in this case, I will substitute R as plus 100. So it's a virtual center of curvature. And when I substitute U to minus infinity or mod U to infinity, the value of V I will get by definition is the focal length. So again, doing that in the question, I mean in the formula here, you can see you'll get focal length as R by 2. But in this case, that means the focal length is plus 50 centimeters. So it is, as we said, it is a virtual focal point behind the pole. So I'll just leave you for a moment with the diagram, but it's pretty self-explanatory and it's pretty simple. Okay. Yes, Ampriti, that is correct. We can use the property of exterior angle, and from that we can construct a triangle which will come out to be isosceles and all that, and from that you can do the derivation for both the parts, for concave as well as convex. But the important thing is now, with this derivation, we can reduce our formula, our UV formula, to a even more generalization kind of thing. So for spherical mirrors, now our UV formula reduces to this. So for all spherical mirrors, now we can reduce our formula to 1 by V plus 1 by U is equal to 1 by F. It becomes more generalized like this, where F is by definition R by 2. And you just keep in mind that a convex mirror has a virtual focal point, because it has a virtual center of curvature, and a concave mirror on the other hand has a real focal point. So it is in front of the pole, this one is behind the pole, the virtual. So if you just keep this property in mind, you're pretty good for the mirror formula engine. And that's how we derive, not only derive, we define the focal position actually. Okay, so it's not just about the derivation, It's also about the definition, what we mean by the quantity focal length, okay, and focal position. Okay, next from this we will see how we can do analysis, or we can do image construction for extended objects. Okay. And with this, we also bring the concept of magnification, okay, and inversion or upright. Okay, whether the image is inverted or it is upright, we understand that concept also. So let us start by taking an example of a concave mirror. So if we have a concave mirror and we have kept an object which is of a certain size, so we cannot treat it as a point object anymore. Again, it's not so large that it's comparable to the radius of curvature or anything like that, because then some of the rays, some of the significant rays coming from it will become, you know, what we call the, so this is the center of curvature, they will become non-paraxial rays. So remember, we have to consider only paraxial rays for image production. Now let us consider our object as something like this. Let's consider our object, for example, here. And again, in the diagram, I'm showing it as slightly large, but you have to imagine that actually it's much smaller. Or at least you have to understand that, you know, what I mean to do here is draw an object which is extended, but its height is very small compared to this PC, very small compared to this, the radius of curvature. Okay. So let's say this object, I label it AB. So now let us consider the rays which are emanating from this object. So now, before I get into this, we will understand, for the sake of ray diagrams, we'll just understand some general principles or some general guidelines for ray diagrams. Okay. And these are applicable for all types of spherical mirrors, as I'll show in the next thing, for ray diagrams. Or you can say ray tracing. Okay. So in general, if you trace any two rays, they will give you the image of whatever you're looking for, because you know they will either intersect to a real point in front, or they will diverge in such a way that those reflected rays, those divergent reflected rays, when you produce them back, they will give you the virtual image. Okay, but sometimes it becomes difficult to draw one type of ray, so we should have some options. Okay, so the first type of option is any incident ray parallel to the principal axis. Okay. After reflection, okay, converges to the focal point. In the case of concave, which I am writing above, or diverges such that it appears to come from the focal point. This is in the what. So what I'm writing in the case of bracket is what we're going to discuss next, the convex mirror. But in the case of concave mirror, as we just seen in the diagram before, any ray which is parallel to the principal axis, after reflection, it will have to go through the focal position. Okay, so let us just trace that particular ray over here. So let us say this is our first type of ray, and immediately after reflection, what it will do is we'll take this kind of a path. Okay, so just hang on with me for a second here. I will. All right. That's the first type of ray that we should be mindful of. And as I told you, to find the image of any point, any two rays are sufficient. Okay? But we will have some more choices also for us. Okay? Now the second is like an inversion of this. So it's like this, that if an incident ray passes through the focal point, or in the case of the other type of mirror, it appears to pass through F, okay, when produced behind the pole. Okay. Then after reflection, it becomes parallel to the principal axis. Okay. So this is in conjunction with a very simple principle in reflection, which is the principle of reversibility. So if I had a situation, if just imagine I had a situation where this was actually the incident ray, then this would be the reflected ray. And see, it just follows the principle that I've just notated below, that any incident ray which is passing through the focal point after reflection, after suffering reflection, what will happen? It will become parallel to the principal axis. Okay. So I will just draw a different ray now, which will demonstrate this. So I'll draw it with a different color, let's say. Okay. And now I'm talking about this particular ray. I'm talking about this ray, which appears to pass through the focal point. Okay. So what will happen to this after reflection? The reflected ray will have to become parallel to the principal axis. So it will have to become something like this. Okay. So this is my second type of incident ray and its corresponding reflected ray. Now why I said see two rays are enough, because now you see these two incident rays are intersecting at a point and they were coming from which point? B. So that means B's image is here. Okay, so that already tells me in this diagram, it gives me a hint that where should the image be for my particular object which I have taken as AB. The image should be here because the image of B should be below here. So the image of A will be on the principal axis, which you understood earlier. Okay, so this will become the image. So this B prime and this A prime will become what you can see is the inverted, diminished and real image of AB. Okay, and by making more such diagrams and understanding these, it will also become clear to you that in case of reflection as well as in case of refraction, later we'll see, whenever the image is real, it is always inverted, whereas whenever the image is virtual, it is upright. Whereas we can have any type of combination of image versus object, whether it is diminished or magnified. For example, we'll see very soon that in the case of concave mirror, it is possible to have a real and diminished image also, like you're seeing over here. It is possible to have a real and magnified image also, like I will show you later. And it is also even possible to have a real image of the same size but inverted. So that's also very interesting case. And interestingly, even in the case of concave mirror, it is possible to have a virtual image, but the virtual image will always be magnified. So that also we'll discuss very soon why that happens. Okay. So these things that I'm just saying out of experience, that which kind of mirror, what type of images are possible. After we do the thorough analysis, this will be very easy for you also. So you will just know these points at the back of your hand, that if I have this kind of mirror, if the object is located at such a position, what kind of image I can expect. And that is a very big part of geometrical optics, because very often you are doing questions which are just based on some kind of estimation. You don't really have to apply the UV formula and waste the time in exam for getting the exact value and then figuring out all that. Sometimes you have to just estimate that. You have to know the behavior of the mirror with respect to a given type of object. And if you know that, then you can do those matrix match questions, those logical MCQ questions with more options and all that. You can do them not only correctly, but you can do them very fast. So one of the objectives of geometrical optics is that not only it's a scoring subject for you at the JEE level, it should also be a subject where you can save time. So you save time in geometrical optics questions, and you can invest that time in things like electrostatics, where the logic is more complicated, or rotational mechanics, where there's a lot of constraint relations and things like that. Okay. So we will keep this in mind from the beginning, and especially during my doubt sessions, I will show you how to use shortcuts and all this analysis while doing questions. It becomes very helpful. Okay. So anyway, so as I was telling you earlier, there are 4 guideline kind of rays that we will discuss about. Now out of that, I have discussed 2 over here, and usually 2 are sufficient to draw a ray diagram. And typically these are the 2 that we draw. Okay, but just as an auxiliary method or as a corollary or something, as a backup plan, we should have a couple of more types of rays and well understood. So the third type of ray we'll see is a very interesting one. If an incident ray passes through the center of curvature, okay, so then it goes on incidence like a normal ray. So it just retraces its path. So that's a very interesting type of ray. So if an incident ray passes through the center of curvature, or in the case of that convex kind of mirror, appears to intersect at C when produced behind the pole. Okay. Then in that case, then the ray retraces its path. Because why it retraces is because it makes a normal incidence. So let me just demonstrate this to you in a separate diagram. So we are talking about a concave mirror just now. So this is my concave mirror. And let's say this is a center of curvature. Okay. Now I had some object over here, like that object EB. Now from this object, let us say I'm actually drawing a ray which is actually passing through the center of curvature. So I'm drawing a ray like this now. So what will happen is this ray over here is actually along the normal, no? Because you can see at the point of intersection, which is some Q or something over here, this is nothing but this thing, what we call, it is nothing but the normal itself. You know, the ray is actually along the normal. So its angle of incidence is 0, its angle of reflection will be 0. So this is what we mean by it's retracing its path. No? So I'll just briefly draw the earlier two rays also which we have done, so that you understand in context of the diagram what is happening over here. So one ray was, let's say parallel to the principal axis, and it passed through somewhere along the focal point. So it was over here. Was passing through the focal point. So let's say it went through here, and after this thing it became parallel to the principal axis. So now you can see all my set of rays, this one, then this one, they are all very neatly, and when you do this on graph paper properly and all that, they will always very neatly intersect at this point. And that is why it's through geometry itself. In fact, that is why the subject is called geometrical optics, because through convenient geometry you are able to understand the behavior of the light, why the light beams coming from this point B are going to intersect at this point. So if you place a white screen over here, or if you place a photographic plate over here below the principal axis, will actually obtain the image of AB, which is having that property. It is inverted real, and real because you can obtain it on a screen, and it is also diminished, as you can see. Now I'll show you very soon. I'll prove why it is diminished, and we'll get the formula of magnification also. But this is the third type of ray. So the one passing through the center of curvature, this red colored ray was the one that I was interested in right now. It retraces its path. This is the third type of ray. Okay, so I will just leave you with a moment to analyze this information. Okay, and we will get back to the fourth type of ray, and we'll see that through the fourth type of ray we also get the formula of the magnification factor. That is the size of the image A prime B prime divided by the size of the object AB. So as you all know, that magnification factor is actually the ratio of image distance to object distance. So again, we don't really need to draw the diagram and do any sort of triangle analysis and all that to find the magnification. Once we have done this derivation, we'll understand the magnification just comes from a simple formula that it is minus of V by U. And I'll show you why it is minus of V by U, because with the minus sign incorporated, the magnification's algebraic sign tells us that it's an inverted image in the case of real, whereas it's an upright image in the case of virtual. So these are a few of the points coming up. Just take a quick look at this diagram and this point. Then we'll move on to the fourth type of ray. Okay. So yeah, so about the fourth type of ray, in fact, let me tell you and you try drawing it yourself. So I'm just giving you the information about what the ray is, and then you make it in the same ray diagram and see the interesting thing you get out of it. So the fourth ray is the one that is going to be incident at the pole. So imagine a ray coming from that point B. That point is like a point object, Imagine a ray coming directly at the pole from there, and try to figure out what you can say about that ray after reflection. Okay. So a ray incident at the pole, how that behaves. Okay, so it behaves according to, so after reflection, it has a symmetrical deviation. In other words, I'm just restating law of reflection. Angle of reflection is equal to angle of incidence. So in simple terms, this is like this, that we have any ray of light incident like this over here, then very bad diagram, but I'm just saving a bit of time here. So this, so we'll see how we incorporate that in our earlier diagram. Okay. So now from this we will get the formula for magnification. So next thing for us, we want to find magnification factor, which we denote by M. So M is defined as the size of the object, sorry, the size of the image, my mistake, as a ratio of the size of the object. But here remember, the size I'm talking about is the dimension perpendicular to the principal axis. There is also a case of keeping an object, lying on the principal axis so that its length is along the principal axis. For that, there is a separate thing of magnification. I will come to that. Okay? But here it is by size of image divided by size of object. What I mean is, it is the dimension perpendicular to principal axis. That meant. So let us understand how to get the formula of magnification. So let's come back to our earlier situation. So this point is our pole. This point, let us say, is our center of curvature. This point is our focal point. And let's again consider our object as somewhere over here. Now I'm just deliberately making a very large object, but remember that in reality, the size of the object should be small compared to the radius of curvature, because otherwise we can't do all our analysis of considering paraxial rays and all that. So just I'll draw 2 or 3 of the different type of rays that we talked about. This is one type of ray. Okay. Then it's another type of ray is one going through the focal point after this thing becomes parallel to the principal axis. Now what I'll do is I'll draw a third type of ray, which is very important, as the one incident at the pole. So let's consider this one. The ray incident at the pole will do this. It will, if my diagram is very accurate, which I'm sure it is not over here, this diagram itself will reflect what I was telling you earlier about the property of that ray, that its divergence is symmetrical. Angle of incidence is equal to angle of reflection. So anyway, let's just work this out. So this is like this, this is like this. So this angle, let's say theta, should be equal to this angle. Okay. And of course, here the image of this point is this one. So this is B prime, A prime versus E. And I'm considering the dimension of the object to be perpendicular to the principal axis. So it's like this. Okay. And just a few more rays to label also. For example, this was the first type of ray, parallel to the principal axis, passes through the focal point after this. Okay. Passing through the focal point after reflection, it becomes what? After reflection, it becomes parallel to the principal axis. And there was a fourth type of ray also passing through the center of curvature, so that is outside the scope of this diagram, so I'm not drawing that. Okay. But anyway, that will be a ray, passing through C and B prime. So it would have to hit the mirror somewhere over here and come back like this. So I'm not really getting into this. So now we want to find the magnification, okay, which if I write without sign, okay, this is just as a mod of the magnification, it should just be A prime B prime as a distance divided by EB. So this is what I want to find out. And now you can see that there are two similar triangles over here. Okay, so they are very visible in the diagram. So I will just list them out. So triangle ABP, that is a triangle subtended by the object at the pole, for which the angle is theta, that right angle triangle. And similarly, the triangle subtended by the image. So that is triangle E prime B prime P are right angled similar triangles. So you just use the property that perpendicular upon base is equal to perpendicular upon base. So you can see that what we get is, on one hand, the ratio of the size of the image upon size of the object, and on the other hand we get the position of the image with respect to the position of the object. Okay. So what we are getting here is that the magnitude of magnification without any sign is the magnitude of V divided by the magnitude of E. But also the image is inverted. If it is inverted, it means that the magnification should be a negative quantity, whereas real image, okay, so that means V is negative because you're taking U as negative. The image is on the same side as object. So that means with the proper sign convention, I have to write MS minus V by U. So this is the formula for the magnification, and as you can see, I've done the proof for the formula taking into account the concave mirror. Now very soon I will do the derivation taking into account the convex mirror, and I will show you that over there we'll get a virtual image, but the formula for magnification will be the same. It will be minus V by U, and whenever we get a virtual image, it will be upright. And the diagram will also show us that why the virtual image is upright as opposed to the real image being inverted. Alright, so this kind of analysis, people, is quite important. I'll try to diminish this a little more so that you can see the diagram with the similar triangles thing I've shown before below. So that should be sufficient. Okay. Yes, so as you can, just to answer some of your doubts on chat, so in a proper ray diagram, from a given point object B, if I am taking a number of incident rays, not only the 4 type of incident rays that I have taken into account here for my analysis, but any incident ray, as long as it is paraxial, after reflection, it will have to pass through that point B prime. B prime becomes the real point of intersection of all the convergent reflected rays because it's a concave mirror and it is giving me a real image. So all reflected rays are convergent and they are convergent to their common real point B prime. So particularly these 4 types of rays are very easy to draw geometrically and show that they converge. All this is of course in context of what we have learned earlier, which is the derivation of the UV formula, which came from that whole alpha, beta, gamma, triangle analysis, small angle approximation and all that. You see, the key to everything is understanding that point, that in that derivation, we were able to show that all paraxial rays are giving us a sharp, well-defined image, whether that image is real in the case of concave over here, or it is virtual in other cases. Alright, people, so I think this should be sufficiently clear. Okay, these derivations are all there in a lot of detail in Resnick Halliday with proper explanation and everything, and they are also there in short in HCV. So if you want a quick reference, they are there. And of course, you will have my whiteboard notes and all that to refer to later. So what I would really suggest is that you do, the derivations yourself once. after going through my lecture notes or after just going through HCV or anything, even your module. And in fact, when you are doing the revision or your own derivation, what I would suggest is try to take cases which are different to the ones which I have taken. Like see in my ray diagram, you'll notice that for this demonstration, I've taken the object beyond center of curvature, and that's why I'm getting a diminished image between center of curvature and focal point. Now, when you are doing the repeat of the derivation at home, take the object over here between C and F, and you will see you will get the reverse principle that the image will go beyond the center of curvature, and that time it will in fact be a magnified and real and inverted image. So that way you will get a lot of experience in drawing ray diagrams. So anyway, now let us look at an example of a convex mirror and understand magnification in that. So first of all, I will just briefly look at the ray diagram guidelines, ray tracing in context of this thing, convex mirror. Let's say this is my principal axis. This is my convex mirror. This is my virtual center of curvature. So this is my virtual focal point, and this is my pole. So let's now trace all the 4 types of rays that we were talking about earlier. So for example, the first type of ray is the ray parallel to the principal axis. Let's say such a ray is incident over here. Then after reflection, it will diverge in such a way that it appears to come through the focal point. It will not pass through the focal point, but it will diverge that it appears to come from the focal point. So that's what we meant in that language over there. This is what it's going to look like. And the second type of ray I was talking about was the ray which appears to be incident at the focal point. So after reflection, it becomes parallel to the principal axis. So that type of ray here is very interesting. It's a ray that would be something like this. Let's say, if you produce it behind the pole, it appears to intersect at that virtual focal point. So this is your incident. It's not actually going and meeting the focal point, but it appears to. Then what will happen is after reflection, it will become parallel to the principal axis. So you can see that if you just apply reversibility on the first ray that I have drawn, the red colored one, is the same thing. This ray, after reflection, will become parallel to the principal axis, right? That is the thing. Okay. Then the third type of ray that we are talking about is the ray which is this one, through the center of curvature. Okay. So if we now consider a ray which is something like this, so just imagine don't worry about the fact that it appears to be passing through that other ray. Doesn't really matter. I'm just focusing on this one right now. Extend it a little bit. So this ray, again, it doesn't really go and meet the center of curvature, but it is, it's just incident in such a way that it appears to be, if you produce it behind, it appears to be. Okay. So what will happen over here is after reflection, it will just retrace its path. It will just, because it's normal incidence. And of course, the fourth and final type of ray is, let us say, this kind of ray, which is incident at the pole. Oops. Okay. So let me try and magnify this a little. Yeah, so maybe something like this. So this is my fourth and final type of ray. Incident at the pole, it diverges symmetrically. So this angle theta will be equal to this angle. That is the idea. So any combination of these 4 rays is enough for my image construction. any type of any combination of 2 out of these 4 if you select, then the ray diagram method will give you the position of the image. So actually we will always use the UV formula for the position of the image, but the ray diagram will help us understand why the image is formed at that position according to the formula. Okay, so hope this is clear. So using this now, let us take an example case and understand the magnification and the virtual nature of image form for an extended object. So next up, I'm again considering the same situation. This is my mirror, this is my pole. Somewhere here is, let's say, the focal point, and somewhere here is the center of curvature. Now let us consider any arbitrary object which is present somewhere here. So let's consider an object EB, let us. And let's try to do the image construction using the guidelines that we've just learned. Okay, so let me draw the most standard one, which is parallel to the principal axis this way. So it is incident here. After reflection, it will appear to diverge such that produced back it meets the focal point. So this is my first step. Now, just for convenience sake, let me take the second one, which is directly the one incident at the pole. So it will just give me a very convenient way of doing the image construction. So this will, after reflection, have to be such that angle of incidence is equal to angle of reflection. So this angle theta should be equal to this angle theta. Now, as you can see, immediately you're getting divergent rays. The 2 reflected rays that you're getting, this blue colored one going back like this, and this green colored one going like this, they are divergent. So they appear to come from a point behind. So next what we have to do is, we have to produce this very reflected ray that we have seen, we have to produce it backwards. So again, this is not an actual ray of light. So this point here becomes the virtual image of B. Okay, so hope this is clear to all of you. Okay, how we've done the ray tracing. So this thing, this point becomes the virtual image of B, and this will be the virtual image of E. So A prime B prime, you can see, is the virtual upright, and from the diagram you can estimate it is also diminished image. Of E. Okay. Now, of course, we can draw the other rays also and show that they will also intersect at the point B prime only. Okay, and I'll do that also just as a reference. Okay, but that's not the point. That's not really necessary here. Okay. So once again, for magnification, you can see that you have 2 right angle triangles which are congruent. So first, let us derive the magnification formula. So once again, triangle EBP, that is a triangle right angle subtended by the object, and A prime B prime P. They are congruent because this angle is the same as that angle. Okay. So, and triangle E prime B prime P, they are again congruent right angled triangles. So you again have that same formula, EB upon AP is equal to A prime B prime upon, okay. And that will give you exactly the same formula till the point that we actually incorporate the sign convention. Even then you will see the formula remains the same, because this time I want the algebraic sign of magnification to be a positive quantity, okay? Because you can see it's an upright image, so the algebraic sign should be positive. Whereas this time you can see V is positive and U is negative. So next step, when you see E prime B prime upon EB becoming equal to E prime P upon EP, you understand that your magnitude of magnification is magnitude of V divided by magnitude of E. And sign convention wise, you understand that this time M should be positive because it's an upright image. Whereas by proper sign convention, V is positive because it is a virtual image, and U as usual is negative. So your formula for magnification still has that minus sign, which is why I said that it's a universal formula. Whether it is virtual image or it is real image, whether we are dealing with concave mirror or convex mirror, the formula is generic. So I'll just leave you with this for a moment, and then I'll also show you a couple of other interesting rays which will give us the same position of image and all that. But actually, this is more than sufficient for our purpose over here, which was to find the magnification, the formula for magnification. So from this point onwards, we don't do magnification by diagram and geometry and all that. This we have the formula derived for us, just like we have the UV formula for the position of the image. Like that, we have the magnification formula for the size of the image. So for an extended object, we find the position of the point A prime, that is V, by the UV formula. 1 by V plus 1 by U is equal to 1 by F. And we find the size of the image, that is A prime B prime, by using the magnification formula. So this becomes very convenient stuff, and it's not only used for the position of the image for a given object. If we have this position to the mirror is nothing but how our V is changing. So it's the same concept. Yeah, I'm getting some messages about something going wrong. Is it? Yeah, I know the video froze in between. A little bit to do with internet connectivity. You know, sometime around 4 in the evening, I've seen the bandwidth goes poor. So maybe people wake up and just start watching Netflix a lot. I don't know, but it should be fine now. Okay. So I'm assuming the whiteboard is clear to all of you. You are getting this, okay, because I'm monitoring it on a different screen. So I'm hoping what I am seeing it is the same as what you are seeing it. I'm actually logged on via 2 different accounts so that I can monitor what you are seeing at your end. So anyway, as I was saying, let's go back to the diagram and try to trace those other type of interesting rays also before we move on to the next thing over here. So in the same diagram, if I want to also show this B prime by a couple of more types of rays, so I'll select first of all that ray, the one which is passing through the focal point when you produce it forward, and therefore it becomes parallel to the principal axis. That very interesting type of ray. So imagine, very good, thanks guys. No issues with the whiteboard, so that's good to know. So you talk about this ray now, which if you keep producing it forward, it should pass through the focal point. So, yeah. So this one. So what should happen to it after reflection? It should become parallel to the principal axis. So very interesting. After reflection, it should become parallel to the principal axis. So in a very good diagram, you will see that so these 2 points should actually almost merge. So I'll try to make that happen. A bit of manipulation on my part. almost. You can see that that's happening in my diagram. So you see what's happening here. My incident ray is actually this one. My incident ray is this one. Okay, and it appears to be going to the focal point right over here. It appears to be going to the focal point, but after reflection, it becomes parallel to the principal axis. So again, now if you, for example, compare as your guideline, you compare two reflected rays. Like you compare this reflected ray and you compare this reflected ray. They are divergent, so they have to be produced back. So when you're producing this divergent reflected ray and the yellow colored divergent reflected ray, you can see that they are tending to intersect at this point over here. So again, B prime becomes the image of that. Okay. Like that, if you do a ray which is appearing to pass through the center of curvature, you will see that that ray also appears to pass through the point B prime because it goes undeviated. So that's the very interesting part of the ray diagrams over here. Okay. And again, see, ray diagrams are very interesting and also very important because you will keep seeing some problems at the JEE Advanced level which are ray diagram based, which you will understand which ray to select or which option to select only if these geometrical aspects are clear. In those particular type of problems, your UV formulae may not help. Okay, it is the proper understanding of the ray diagrams only which will help you understand which of the options for the reflected ray or which of the options for the geometrical situations given is correct. So it's very important that you understand this thing properly. Okay, so that's about these ray diagrams and things. Okay, so now from this, what we'll do is, before we jump into problems and all again, we will do a general analysis of both the types of mirrors. Okay, so that will help us understand what these formulae tend to give us in different type of situations. So we will do a general analysis for spherical mirrors. Now in this, I will take some general type of examples and show you what kind of images those general type of examples of objects take. And in some cases, I will do actually a numerical calculation and show you. And some cases, I will not do the full calculation. I will just justify with the ray diagram. But again, what I'd like you to do is when you are doing revision at home, you support my ray diagrams and my general principles with some kind of examples and calculations. So you can just take. So I will start with the analysis of the concave mirror. So the first aspect of concave mirror, we have seen that if the object is at infinity or mod u is infinity, whatever, the image is at the real focal point, okay, in front of P. And now you can imagine by the UV formula, by the magnification formula, it is highly diminished because your image distance is finite. Remember, f is equal to r by 2. So your image distance, b is actually minus of whatever the radius is in centimeters divided by 2, whereas your object distance is tending to infinity. So your magnification factor is almost tending to 0 as u is tending to infinity. So it is highly diminished. Okay. Real and inverted. So for this, I don't need to draw any ray diagram, just the analysis of what the definition of focal point was. That was telling me. Okay. Now, second one, I'll see if the object is in between minus infinity and the center of curvature. So here I'll just support it with a numerical example. The ray diagram you already understood because this is the example we took in the case of the explanation of or the derivation of the formula of magnification. This is actually the physical example we are taking. So focal point, center of curvature. Now if my real object is somewhere over here, let's say like this, then already from ray diagrams and all you have understood that this thing will be somewhere over here. So we will get what is called a real inverted and diminished image, okay, between center of curvature and focal point. Okay. So in fact, it's a very interesting thing. You will realize by using relative motion concept also, if your object were to move in this direction, then your image would move in this direction. You could understand that with examples also. When the object was at infinity, your image was highly diminished at the focal point. By the time your object has come from infinity to a little here, your image has moved like this. Okay. So that's another thing to understand. So let's just take an example. So suppose in our example, the radius of the mirror is 120 centimeters. And we take the object distance, this is the pole. So we take the object distance as, let us say, something 360 centimeters. Okay. So you see what you are getting for the magnification and you are getting for the image. So 1 by V plus 1 by U, which over here will be with sine minus 360, should be equal to 1 by F with sine which is minus 60, because F is R by 2. So you can see that you will get V like this. 1 by 360 minus 1 by 60. Okay. So that should come out to be minus 5 by 360. So which should come out to be minus 72 centimeters. Okay. So you can see that this is between center of curvature and focal point, because center of curvature is at minus 120 and the focal point is at minus 60. And you can see that the magnification factor, which is minus V by U, is minus of minus 72 divided by minus 360. So that's how much. So minus 0.2. Correct. So I'm just going to zoom out a bit so that you can see this. So like that, you can take different values. Like I've taken AP here 360. Next, you can take it 300, then 240 like that, and you'll see the trend of what I've written over here. As the object is moving towards the center of curvature, you will see the image from the other side will also move towards the center of curvature. And as you'll also see that as the object comes closer and closer to the center of curvature, the size of the image increases. So the diminished factor, which is minus of some fraction, that fraction comes closer and closer to 1. Okay. So in fact, the special case we'll see, when your object AB has reached the center of curvature, your image A prime B prime will also reach the center of curvature, and you'll get a magnification factor of exactly minus 1. That means the image and object are lying in the same plane, but the image is just vertically below the object. Okay, people. So you can also support this with a ray diagram, which will be very similar to the ray diagram we had got earlier to derive the formula of magnification. So I'm leaving that to you to work out. Okay. So the next case, I will actually treat it like an extension of this, that as we are discussing, as your object is coming like this towards the pole, your image is going to move like this from F towards C. So you will see by formula also that when the object exactly comes to center of curvature, the image overlaps with it. But it doesn't overlap in that sense because it's a diminished image. Okay, so see the third case, if I write over here, the object is at center of curvature. Then the image will also be at center of curvature, but we'll get the magnification factor as minus 1. So it will be a same size inverted real image. Okay, so just roughly your ray diagram will be something like this. if your object is here, then you place a photographic plate here below it, and you will obtain its image like this. And you can see you will get this by substituting u equal to minus of the radius, or u equal to r. If you substitute, you get v also as r by 2. You substitute with sign convention, you get this in the uv formula. Now the next step you will see is actually like a, you can say it as a reversal of the earlier ray diagram. Which one? Where the object was between C and infinity. So now if the object is where that image was, okay, so that is between center of curvature and focal point. Now you will see the image is where that object was, beyond center of curvature, like this. Okay. So this is just a reversal of, if you invert the role played by object and image over there in the previous ray diagram, in the second case that we discussed, you will see, you will understand this very nicely. You just imagine that that image that we have taken A prime, B prime is actually your object. Then you will see that the object we had was actually your image. But I will draw the diagram properly here, with the object being on the positive side. Though there is no hard and fast rule, the object can be on the below side, and the image will come up on the upper side, like that. So let's just, as a practice, let's look at this case with the ray diagram also. So in this case, what we will get is, we will get a, not only will get an upright, an inverted real image, which will be somewhere here, but it will also be larger in size. So I will just draw two of the rays, the primary ones, which are easy to draw. Okay, so this one, and let me draw the one which is passing through the focal point. Okay. And if you like, you can just draw another one also, like the one passing through the pole after reflection. Anyway, so coming back to this, this one is like this, incident reflected. That one is like this. Okay. So as you can see, the image of this has now appeared here. If this point was B, then its image has appeared over here, B prime. So we are getting this. So this image that you can see, it is real inverted, but this time it is magnified. It's larger in size. So that is why I told you that concave mirrors are capable of producing both diminished and magnified virtual images. And you can try an example. You can try an example like this, where if you take the radius as, let's say, minus 90, and you take the object distance as, let's say, minus 60 or something. So focal length you can see is minus 45. So you'll get the V, which will show you this. 1 by V plus 1 by U is equal to 1 by F. So let's see what this gives us. So V here will come out to be 60, and 45's LCM will be 15 3s are, 15 4s are, so correct. I hope that calculation is correct. So your magnification will come out to be, object distance was 60 and 180, so minus 3. So the image will actually be, so this diagram is actually not pertaining to this one. In this one, that the object should be actually closer to the focal point, so the image will be somewhere here, further away. But anyway, you can try out some values yourself when you are revising this part. And actually, you'll see that just by doing some calculations like this yourself to understand the derivations, you will get very quick at geometrical optics calculation based questions. And then all the questions where there's the combination of mirrors and all that will become very natural for you, because you'll know where to expect what. Alright. Now in this diagram also you'll understand the trend over here. If the object is moving further towards the pole, the image will continue moving backwards towards infinity. Okay, so you can see this trend is continuing from earlier. From infinity the object started, the image started from the focal point. So object is coming from infinity towards C, the image is coming from F towards C. Then at C they cross each other, the object now goes past C continuing towards the pole, the image goes past C on the other side continuing towards infinity. And finally when your object reaches the focal point, that is when your image has gone to infinity. So in that case, it's a very, very vastly magnified. So it's not going to be a very well-defined image because it's hugely magnified. The rays are just becoming kind of parallel to the principal axis when the object is at the focal point. So it's not really of any use to us, that image. So next point here. Which I can say was probably 5. When the object is at the focal point, you will see that the image is very distant. Okay. Your V will tend to infinity. So it is not a clear image at all. Now what is basically happening is that the paraxial rays, the paraxial incident rays are parallel to principal axis after reflection. After suffering reflection, that is what happens. So you don't really get any usable kind of image. You can't really obtain that image on a photographic plate or something like that. There is something we can do with such an image, we'll discuss later, okay? But for that we need a second stage. If we make those reflected rays then go through a converging lens or something like that, or another concave mirror reflects them to a real point in front of it, then we might get a usable image. But right now, just on the basis of those reflected rays which are becoming parallel to the principal axis, it's not really anything of use to us. Alright people, so hope this is clear. So now we come to the interesting situation where if the object goes beyond the focal point further, what you will expect to see is that the rays, they are incident in such a way that you'll now realize that reflection actually causes them to diverge. So that is the only situation in which a so-called convergent mirror, which is a concave mirror, actually gives you a virtual image. So what I would like you guys to do is consider the next thing yourself and start making the ray diagram. I'll put it up on the board. So consider, so let me give you a situation and try to first draw the ray diagram, and then we'll come to the calculation on that. Okay. So we'll take the situation where the object now is between the pole and the focal point. So take an example and try this out. And in the example, try the ray diagram first, then come to the calculation. Take the example where the object distance, okay, is at, let us say, 45 centimeters in front of the pole. Okay. And it is a concave mirror, as we are discussing, of radius, let us say 120 centimeters. So the focal length is 60 centimeters. So as you can see, my object distance 45 in front is less than the focal length. So it is ahead of the focal point. It is between the pole and the focal point. So just try this out with a diagram and then with the calculation. Yes, very good. Yuvanshi, you are correct. Your analysis is correct. Good, Sudhir, you also got it correct. Yes, Manishka, you are correct. So let me first make the estimated ray diagram. Yes, Ganesh, correct. Very good. So pole here, focal point here, let us say, center of curvature over here, let us say. And my object is somewhere here, let us say, because I had taken 45 centimeters, whereas the focal length was 60 in magnitude. So assume something like this. Okay. So first of all, let me apply the principles of my ray diagram concept. Then I will come to formula and justifying it by formula and all that. So what should happen here, according to my this thing, that a ray which is parallel to the principal axis should after reflection pass through the focal point. So this is one type of ray. Now let's consider another type of ray as any one of the examples we used to. So let's consider a ray. Now it's going to be very difficult to draw a ray which appears to be passing through the focal point, because that ray will tend to be like this. It will tend to be like this ray. So I'm not going to get into that because my diagram is kind of going outside the scope of paraxial ray. So let me consider the other type of ray, which is incident at the pole. So that will become symmetrical after reflection, like this. Let us say. If my diagram is correct, then you will realize that this reflected ray, the green colored reflected ray, is ever so divergent compared to the red colored reflected ray. They are not going to meet somewhere further because they are divergent from each other. So that will be able to further explain if we just produce these back and understand that they will tend to meet at some kind of point behind. Okay. So those of you who understood the diagram, you can continue with the calculation also. So this reflected ray has to be actually produced back to understand where it goes and intersects with this one. Might intersect somewhere here. Let's say the intersect somewhere. So that is why what is happening is my final this thing image will tend to be somewhere here. So you'll see that interestingly the diagram is very similar to the convex mirror case we had taken, but at the same time it's not exactly similar, it's different because the focal point is real, the center of curvature is real, but it's just the way the rays are behaving. Even though the rays are actually made to converge because of the reflection, but the rate at which they're converging is not the same, and in fact this one dominates over this. So that's why they are actually divergent with respect to each other. they are converging onto the principal axis, but they are divergent with respect to each other. So they appear to be coming from this virtual point behind. So that is why you can see over here that E prime B prime becomes the virtual, okay, upright and magnified image of AB. So that becomes a property of the image whenever we have this kind of situation. When we have this kind of situation, our image has this property below which I've written. It is always like this. Virtual, upright and magnified. You will understand after this situation that a concave mirror cannot give you a diminished virtual image. If it is giving you a virtual image, it has to be magnified. And with the next stage, we'll understand that if you are having a diminished virtual image, it has to be a convex mirror. It will not be a concave mirror. So these are, important little factors to keep in mind when you are solving those conceptual type of questions. And if these various cases are clear to you and you keep revising them before you, sit down to do a lot of problems and all, you will see that these things become very natural for you to understand. Okay. So let's also do with the case of the example we had taken. So in the example we had taken, our focal length was minus 60 centimeters with sign convention. Our U was minus 45. So we'll see what we'll get as our V. We get 1 by V plus 1 by U is equal to 1 by F. So we are getting V as plus 180. So that is showing you that first of all the plus sign is showing you that it is this thing. It is virtual. Okay, and magnification will show that it is magnified and upright. Okay, so minus V by U will, as you can see in this case, become 180 or minus of 180 by minus 45. Minus of plus 180 by minus 45. So the image will be 4 times in size, but upright. Plus 4. So upright image and 4 times in size. Okay, or 4x zoom, you can see that kind of image. So I'll just leave you for a bit with the calculation and the diagram. And for the moment, this is the complete analysis for the concave mirror. Why I'm saying for the moment? Because you see that we have covered every position of the object from infinity right up to the pole. Because next we'll see if you bring the object right up to the pole, the image also comes up right up to the pole, and they are basically just adjacent of each other, the object and the pole. But we have covered only what is called the real space for the object. We have covered every situation in which you can keep an object in front of the mirror, right from infinity right up to the pole. So that is the situation for real objects. Now we will also at a later stage discuss about virtual objects, something that we had started the discussion about last time. Alright people, so this was the complete detailed analysis of the concave mirror for real objects. We will come back very shortly to the concave mirror for virtual objects also. But in the meantime, let us also understand the analysis for the sorry, that was for concave, and now we are going to do for convex mirrors. Okay, so as you know, you probably know from experience, there's only one type of image that you get for convex mirrors, and that is virtual and diminished. There's no question of any other type of image unless it's a virtual object. Okay, remember in today's discussion till now, we are talking about real objects only. So anytime we have a convex mirror like this with a virtual focal point, let's say over here, and a virtual center of curvature over here, and the pole over here. So it doesn't matter what the distance of the object is on the other side, whether it's at infinity or close to the focal distance or close to the radius in terms of all that. It will always give us only one type of image, and that's what I'm going to discuss here. It will always give you a situation where a ray diagram is something generic like this. Parallel to the principal axis, passes through the focal point, or diverges such that it passes through the focal point. And let us consider another ray, which is let's say through the pole. So it diverges off symmetrically. So I'm just drawing a bit of a generic kind of diagram. Yeah, that seems okay now. So you can see in this diagram that any sort of any sort of object, irrespective of its distance from the pole, will always tend to give you an image which is in between these 2 points. That is in between the pole and center of and focal point. Okay, somewhere over here, you will tend to get the image. So any object EB that is u from minus infinity to u tending to 0. So you bring the object right against here also. The image will be right against over here. So the image will be of this type. It will give you a virtual diminished and upright image. Okay. So this is a like almost a word play. Anytime you have a magnified virtual image, it must be coming from a concave mirror, because a convex mirror cannot give you that. Whereas anytime you have a diminished but virtual image, it must be coming from a convex mirror, because a concave mirror cannot give you that type. Okay, so this is something important to keep in mind. And you can just take some examples and check this. So from those examples, you'll also be able to check that the trend of motion is like this. If the object is moving like this, the image will move like this. And in this case, the only position where object and image can coincide is when the object is right against the mirror. So it's like, when you are standing right against a plane mirror, how your image looks. It looks right, it's right against you. So imagine as an object, you are right against a spherical mirror. For you, the spherical mirror has become a plane mirror at that point, because the radius is very large compared to the object distance. So it's basically just like a plane mirror. When you are right against it, what happens? The same thing will happen when this point of when this object is right against the spherical mirror at the pole P. Okay, so very simple analysis. Only one type of situation for real objects for the convex mirror. Okay. Now I'm going to quickly go through the analysis of virtual objects for concave mirror. Okay. And there's a lot to learn through that actually. So next thing is very important and kind of a little bit more towards new things for us. Okay. So we will next look at analysis for a virtual object for concave mirrors. Okay. So first of all, let's just try to understand what we mean by a virtual object. So whole focal point, center of curvature all right. Now suppose my incident rays are something like this. These are all my incident rays. Okay. Such that they are actually not coming from some real point in front, but they appear to be intersecting at a virtual point behind. Then that point where they appear to be intersecting, when you forcefully produce them back, that imaginary point where they appear to be intersecting, that is called the virtual object. So this is an example of virtual object. So this is a virtual point object. Okay. So here what will happen to the rays as a result of reflection is that they will give you a real image somewhere over here. Because again, if you just think in terms of laws of reflection, so this is your normal at this point. So this ray will tend to do something like this. This ray will tend to do something like this. This ray will tend to do something like this. So the reflected rays here will be this, this, and this. In fact, let me just try and make it a little easier to understand by color coding these. Something like this. Okay. Similarly, yeah. So we are always considering paraxial rays. In my diagram, to answer your question, beta, in my diagram the rays don't look paraxial at all. Okay? But remember that is just a rough diagram. So what we are trying to consider over here is paraxial rays. Just imagine that the angles involved are very small. So just imagine that you compress the diagram in your mind a lot. Okay. So now let's try to understand this with a calculation. Okay. So anyway, coming back to this first, so what we can see is this point where they intersect in front. This becomes the real image. So I becomes a real image for the virtual object O prime. Okay. Now let us try to understand the location and all this of this by understanding reversibility. So just let's do one thing. Let's apply reversibility principle over here. Okay. Applying reversibility. Okay. So for my convex mirror, for my concave mirror, just try to think. We've just discussed about this. What type of object gives you an image over here, which is virtual? Now, what is the object in this case? So, and you will recall that the object has to be between the focal point and pole. You realize it's an object somewhere over here. This type of an object, yes, correct, gives you an image over here. Why? Because this is what happens in terms of the ray diagram. is what happened. So now just think of reversibility. So what I'm doing next is, if I make I the object, then what does O become? It becomes the real image for this. If I just apply the principle of reversibility to these rays, something like this happens. This is the incident ray, this becomes the reflected ray. This becomes the incident ray, this becomes the reflected ray. And that is what maths will also tell you. Okay. So we see that any object, real object, which is between pole and focal point, between focal point and pole, gives you a virtual image. Between plus infinity and the pole. Now try to understand why I'm saying this. Plus infinity and the pole. Because remember, when your object is right at the focal point, where is your image? It's at infinity. The rays have become parallel to the principal axis. So the moment your object comes somewhere over here, just to the right of the focal point, where does your image appear? Very, very far away on the real, on the virtual side. Okay. Then as the object comes closer like this, where does the image come? It comes closer to the pole. Then as the object comes further closer, the image comes further closer. And by the time the object has reached here, your image has reached here. So the entire virtual space for image, the entire virtual space from P to plus infinity is covered by this very small space for object, which is between focal point and pole. So when you apply reversibility now to this, you will see that the reverse is true. That for the entire virtual space for object, the image is in a very small real space that is between focal point and pole. So apply reversibility here. And you will understand that for any virtual object, because we are covering the entire virtual space over here, we are covering the entire virtual space here. So any virtual object, okay, from plus infinity to pole, we get a real image. Okay, between only these two, okay, between focal point and pole. And that real image will be inverted. Oh, sorry, it will be upright. Now this is the thing where, you know, even for a moment, see, I got confused. It's a real image, but at the same time, it is from a virtual object. So interestingly, it is going to be upright. And I'll show you in a ray diagram why it is going to be upright. Okay, it is going to be upright, diminished, and reversed. Okay, so just note down this concept of reversibility, and then through a ray diagram, we'll understand. And now, you know, gradually we'll get more and more comfortable with the idea of virtual objects. All right, so there is only one case for virtual objects as far as the concave mirror is concerned. As you can see in this note that we've written below, any type of virtual object, whether it is at infinite distance from the pole or right behind the pole, as far as a concave mirror is concerned, it will only give you one type of image, and that will be a real image in front of the pole, but between the pole and focal point, and it will be upright and it will be diminished. And let's now support this with the ray diagram. And just to tell you what I'm doing in the ray diagram, you will realize that the ray diagram I'm going to draw is just the reversal of this. In this ray diagram that I've got over here, just imagine that these rays are the incident ones, the ones which are actually appearing to intersect at this B prime. So this B prime is actually like the virtual object. So its real image is going to be over here. So that is the explanation for why this happens. Okay. So let's understand this with an example which is both numerical and diagrammatic. Okay. So let's take an example like this, that rays incident on a concave mirror converge when produced behind it to form a virtual object, which I'm in the diagram labeling suppose as EB, at, let us say, 90 centimeters behind. Okay, and the size EB, let us say, is 6 millimeters, and the radius of the mirror radius of curvature of the mirror is, let us say, 60 centimeters. Now we want to find the position, size, and type of image. So first, let us try to understand what we are dealing with over here in terms of a diagram. Then we'll come to the calculation part and we'll show how both support each other. So what we are dealing with is something like this. This is my principal axis. This is my concave mirror. This is my focal point. This is my center of curvature, let's say. This is the pole. Now, just to help me a little bit, I'll also draw a symmetric point behind, which is not really important just now, but in lenses this becomes more important. So the C prime is symmetric like this. Okay. Now, what was the radius of curvature? It was 60 centimeters, whereas the object's distance was how much? It was 90 centimeters. Okay. So I will just have to extend this line a little bit. Okay. So now what is happening is my incident rays are such that they kind of appear to give me, a virtual object somewhere. So this is not something that really exists. Okay, it just appears to be there. So I'm again going to show it like a broken kind of thing like this. Okay, now how is this virtual object AB actually coming? It is coming from these kind of rays. It is coming from rays which are, now let us consider a ray which is parallel to the principal axis. So that incident ray is something like this. Something like this. When I produce it all the way back, it's like this incident. Okay. Whereas actually it's incident only up to here. And we know that after reflection, what will happen? It will suffer reflection and pass through the focal point. So actually, this incident ray will do this after reflection. It will do this. Okay. Now again, let us consider something like this. Another ray, which when you produce it back, it appears to meet at the point B. This other incident ray. So this time, let us consider a ray which goes through the pole and appears to do that. Okay. So let's consider an incident ray like this one. So this is my incident ray. Okay, but remember that it doesn't actually go all the way behind. I'm just producing it back. So had the mirror not been there to intercept these two rays, what would have happened? They would have given you an actual point over here. If you placed a photographic plate over here and there was no mirror here, you would have got an image over here. But the mirror is now blocking it, and the mirror is blocking it and doing what? It's reflecting these two rays like this. So this ray after reflection is doing this, as you can see. This angle is equal to this angle. It's doing this. Okay. So now you can see in my diagram, okay, what is actually happening. The two incident rays, that is this one and this one. Without the mirror being present, they would have given you a point object here. But the reflection is causing those rays to get reflected and converge to a real point over here. So what is doing? It's creating a real image of this virtual object at this point. So this is becoming the real image of a virtual object. Very interesting. So this is the real image for the virtual object. And because it is a combination of real virtual, so it is again upright. And in this particular case, it is also diminished, as you can see from the diagram. And again, as you can see from the diagram, it is between the focal point and pole. It is between the focal point and pole. Now, what I want you to do next is, as you're noting down this diagram or understanding it fully, also support what I've done here with the calculation, with the values I've taken about. Because here I've just done a diagram roughly. I've not drawn it on graphic or anything. So there is no value in it. There is no numerical value in it. But you can also find the numerical values involved if you take this distance PA. Okay, so this is telling you that the distance PA should be taken as, what was it now? 90 centimeters. And the distance PC, which is the radius, is 60 centimeters. And also the size of the object AB is supposed to be just 6 millimeters. So that's also how you'll understand my diagram is not correct in perspective, because it's almost like my y-axis has a different scale compared to my x-axis, because that size AB is just supposed to be 6 millimeters, whereas AP is supposed to be 90 centimeters. Yes, let me just check your answer, Ganesh. Yes, Ganesh, this has a use in real life. For example, if you have something like, a reflecting telescope, where there are multiple stages of reflection, including multiple stages of refraction and reflection. So you might be using some optical instrument where you're doing something like this. Light coming from infinity from somewhere is first going through a lens. And that lens is making it converge like this. But then it is going on a mirror somewhere here. So you can see the object, as far as the mirror is concerned, is becoming a virtual object. And then it is giving you a real image somewhere over here. And you are obtaining it on a photographic plate which you place over here. So some kind of arrangement like this is the practical application of this. And if you see the history of geometrical geometrical optics, reflecting telescopes came first, before the compound lens kind of telescopes came, or the combination lens kind of telescopes came. Because technology wise, your very accurately built or very accurately machined spherical mirrors preceded very accurately machined lenses. Okay, so wherever the practical use of virtual object comes in is always in a system of optical components. So one thing will be producing some kind of an image, and that image will become the object for the spherical mirror, and that object for the spherical mirror will happen to be this thing. Okay, how is AP? No, AP beta is 90 centimeters. No, because the object is this. Okay. Whereas PC, that is the radius of curvature, is 60 centimeters. Okay, the radius of curvature of the mirror is 60 centimeters given in the question. Whereas in the question I had given that the virtual object AB is 90 centimeters behind the pole. Okay, behind This should be behind the pole. I mean behind what? So behind the position of the mirror, which is nothing but the pole. So that is why my AP is 90 centimeters or PA is 90 centimeters. Okay. So with this information now, how I will substitute in my UV formula? Let us look at that and how that will finally support the diagram which I've got over here. So substituting the UV formula here, I will be substituting U as how much? I will be substituting U as positive of 90 centimeters, which looks very strange, but remember this is the case of the virtual object. So that's what the incident rays are doing. They are actually converging to a virtual point behind. Whereas my focal length should be how much? It should be minus of, what was it? This was 60, so this should be 30 centimeters. Radius of curvature was 60, so focal length. Okay, so this will now give me 1 by V plus 1 by U is equal to 1 by F. So you can see already that your V will come out to be negative. And it will come out to be negative such that its magnitude is less than 30. Just a little bit of experience in solving these type of problems will show you these things. If you take the minus sign common, or you can write it as minus 1 by 30 plus 1 by 90, whatever. So you will get over here how much? You will get 3 minus 1. So 2 by 30, so you will get V as minus 15. So in fact, you are getting in this case, it's exactly at the midpoint of the focal point and the center and the pole. Okay, so you're getting the magnification factor in fact as minus of V by U. Okay, so that is how much. Yeah, something wrong with my calculation, guys? Image distance is minus 36. What have I done wrong? So radius of curvature is 60. Okay, so this is correct. The focal length is this, and the object distance is plus 90. Oh, sorry. This is becoming plus. Yes, it's correct. Okay, so let's make a correction here. So this is now how much? 3 plus 1, so 4. So it is 90 by 4. So it's 22.5. Just make a correction. Just follow my calculations, guys. Here. See, radius was 60. So R with proper sign is minus 60. So that's how my focal length is minus 30. And the object is a virtual object behind. At distance AP equal to 90 centimeters. So that's why I've taken this. Okay. So substituting this 1 by V plus 1 by U is equal to 1 by F, right? So it goes with the minus sign on that side. So that's why this becomes 4 plus 1, 5. 3 plus 1, 4 by 90 or 90 by 4 with the minus sign. So that is how much? Minus 22.5. Next step, my magnification factor. Okay, so that's correct now, 22.5. Yeah, so calculation is something very painful. Sometimes you have to be careful about these things. So it is how much? It is plus 1 by 4. Okay, so it is upright and 1/4 the size. So I think I had taken the size of the object AB was 6 millimeters. So A prime V prime will become 1.5 millimeters. So this becomes the full calculation of it. Okay, so hope both the ray diagram and the calculation are helping you understand how how a virtual object is in fact giving you a real image. Okay. Now, what I will do is I will leave the analysis of virtual objects for convex mirrors as something for you to work out, and I'll keep that discussion for the next class, and I'll move ahead with refraction. Because a lot of the questions you're doing are going to involve tricks with refraction and all that. So virtual objects for convex mirrors. Now this is something interesting. It will give you a lot of cases. You will see that you will get cases where you get virtual object giving you virtual image, okay, virtual diminished or virtual magnified, okay, both the cases. So you just think of it like a reversibility, okay, and you will understand what's happening. Okay. It can also give you real image. So interestingly, all these cases are possible. Sorry, just my mistake. Here it will either give you virtual magnified, or it will give you real image which is magnified, or it will give you real image which is diminished. So you'll have three different situations which are possible. Okay, so work out the three situations yourself by doing some experimentation with ray diagrams and also doing some experimentation with values. UV formula, just take some different type of values and you will understand. Okay, so for example, if you take something which has a radius of, let us say, plus 60 centimeters, then you take various cases. So this is your center of curvature. So you take cases of like this: u is equal to, let's say, plus 15, then u is equal to plus 20, then u is equal to plus 30, then u is equal to plus 45, then u is equal to plus 60, then u is equal to plus 90, and then just take something very large like maybe plus 360 or something, and you will get the trend. So you will be able to see from this that which of these are giving this, which of these are giving this, and you will understand the different cases. So that is something interesting, but at the same time a little lengthy for you to work out. So you do this as a homework exercise, and you will learn a lot about ray diagrams and things like that also. Okay. So this is more or less about mirrors. Now, a couple of more things about relative motion. In the case of spherical mirrors, we'll see before we move on to this thing. So two types of relative motion we'll see. One is where the motion is happening along the principal axis. Just for reference, I'm drawing this. It could be the other way also. So if I have an object like this, which is moving like this, okay, then in this case, it will give you a virtual image on this side because it's a convex mirror. You'll see it is moving like this. Now, how to get the relation between this? This is how you do. If the mirror is stationary at rest, okay, then the proper VO with proper sign convention is nothing but du by dt. With proper sign, this side is negative, this side is positive. So in this particular case, it is actually minus of du by dt, but u itself is negative, whatever. Okay, and vi is nothing but dv by dt. But here you can see it is the rate at which v is decreasing, and v is a positive quantity, so there will be a minus sign. Okay, so how we get the relation between them is we take the 1 by u plus 1 by u is equal to 1 by f formula, and in this what is happening? F is constant, and we differentiate it. Okay, so differentiation with respect to time. Okay. So So that tells us minus 1 by v square into dv by dt by chain rule. Okay. Minus 1 by u square into du by dt is equal to 0. So this gives us the relation that dv by dt is equal to minus of v square by u square times du by dt. Now again, in the sign convention, the diagram I have taken earlier, dv by dt was actually minus of v of the object. So in this case, the minus sign will cancel out, and v square by u square is nothing but square of the magnification. So this is the simple thing to remember, that if the object is moving along the principal axis in both types of mirrors, the ratio of the speed of the image to the speed of the object becomes square of the magnification. So simple thing to remember. So for both types of, for all spherical mirrors, mod of VO upon mod of VI is always equal to m square. And direction you can just figure out by your analysis. Because you've done such a detailed analysis, so you know that as the object is moving in a certain direction, how the image is moving. So that you can always just figure out from that analysis. Or you can incorporate sign convention in your differentiation term and all that, and it will come. Okay. So this is the first part of relative motion, when the object is moving parallel to the principal axis. So ultimately here VI and VO are, the velocities in these particular directions. So you see, when the object is in fact moving towards the pole, the image is also moving towards the pole. So there is no final formula. Yes, Ganesh, VI is equal to m square times VO. Yes. Oh, sorry, this one. Yes, correct. People just make a quick correction here. This ratio is reverse. Okay. As Ganesh has rightly pointed out, velocity of the image is m squared times velocity of the object, or the magnitude of the velocity of the image ratio with the velocity of the object's magnitude is always m squared. So this is the general rule of thumb. Yes. Okay, now likewise we'll also see what happens if the object is moving perpendicular to the principal axis, and there we'll see the formula, the ratio of the speeds is just m, whereas here it is m square. So that's how, if it has a general velocity, then you can just take components. Take the component parallel to the principal axis as Vx. So the images Vx will become m square times. And take the component perpendicular to the principal axis as Vy. So the images Vy will become m times. Okay, people. Now, the perpendicular one is even easier to understand. There's nothing to it actually, because you can just use the the magnification in that direction, the direction perpendicular to the principal axis as a concept. So this time, let us just, for the sake of variety, take a convex mirror. Now, suppose the center of curvature is here and the focal point is here. The pole is somewhere. Okay. Now, suppose we have an object which is over here. Let's say O. So its image will be somewhere over here. Okay. Now, if the object moves like this with a velocity VO, and after some time it reaches a point like this O prime. So we know that the velocity of the image should be something like this, and after some time it should reach somewhere here, I prime. It's just a very simple principle. Okay, so now we know that if this was an extended object, then the image size divided by the object size is nothing but the magnification with sign convention also. So if this is moved from time t equal to 0 to t equal to delta t, and this is also moved in that same time, then you can see that it is basically v of the image into delta t divided by v of the object into delta t. So it's the same. So the velocity of the image has a magnitude which is actually mod of m times. If you want to just write the magnitude, it is that way. Whereas if you want to get the direction also, the algebraic sign of magnification will take care of this. So the speed of the image perpendicular to the principal axis is the magnitude of magnification into speed of the object perpendicular. Okay, that's without sign convention, and with sign, it actually becomes vi is equal to m times v. So in a practical case where the object is moving something like this, you break it into components vx and vy, and remember that the image will move something like this, and the images vx will become m square times, whereas the images vy will become m times. So that is how we deal with relative motion in this case. Okay, people. So hope this is clear. Yeah. So just to explain to you re-explain what's happening over here. See, imagine in a time delta t, your object has moved from this point over here, okay, to this point over here. So it's like, you have somebody in the waiting room also. Yeah. So it's like now you see if you superimpose the initial position of the object with the final position of the object, it has become like an extended object like this. At the top of this arrow is the final position of the object, and the base was the initial position. So when the object was at the base, the image was here. When the object reaches the top of the arrow, the image should reach the top of the arrow. So if you superimpose these diagrams, this should be the image of this extended object. So the ratio of the sizes is nothing but the linear magnification. So hence, if the object is actually reaching from here to here in time delta t, the image will also reach from here to here in time delta t, and that is the ratio of the velocities. Okay, so hope that point is clear in this. Right. So that is how you can work out questions related to this thing, relative velocity. Now let us come to the next part of our optics, which is going to be refraction. Okay. So refraction is again based on the principle of bending of light as it moves into a medium where its velocity is different, and it follows Snell's law. Okay. Now the derivation of Snell's law from a theoretical principle we'll again do later, as I told you, when we discuss about Huygens principle and its application in wave optics. So for now, you just think of Snell's law as an experimental law. But what does Snell's law tell us? That it tells us that, but before that, let's understand the property of refractive index. So there are two types of refractive index: absolute, like we might denote that with mu, or relative. So we might define that as mu of A with respect to B, something like this. Okay. So let's understand these things first. Then we'll come back to Snell's law. Okay. So what is refractive index for a medium? It is nothing but, for the absolute refractive index for a medium, it is nothing but speed of light in vacuum divided by speed of light in that particular medium. This is how we define it. In what we call free space. So since you've done electrostatics, now you understand what is free space. It is the space where the permittivity of the medium is epsilon naught. And later in magnetism, you'll see that permeability of the medium, the magnetic permeability is mu naught. So the speed of light is given by that formula, which is 1 by square root of epsilon naught by mu naught. But more importantly, its value is 3 into 10 raised power 8 meters per second. Whereas V is the speed of light or any electromagnetic wave for that matter in the medium. So that is how we define absolute refractive index. Now, you also define relative refractive index of A with respect to B. Okay, so this is refractive index of medium A with respect to medium B. So this actually is defined like this. It is VB by B. So for example, I want to say the refractive index of glass with respect to water. So it should be speed of light in water divided by speed of light in glass. Okay. Now I also understand that the absolute refractive index of glass is, let us say, suppose it is 3 by 2 or 1.5. That means speed of light in glass is how much? It is speed of light divided by refractive index of glass. So it is 3 divided by 3 by 2. So it is 2 into 10 raised power 8 meters per second. Okay. And I also understand that refractive index of water, suppose, is 1.33, so around 4 by 3. So speed of light in water is speed of light absolute divided by refractive index of water absolute. So that is 3 divided by 3 by 4. So that is 9 by 4, or a little more than 2. 2.25 into 10 raised power 8 meters per second. Okay. So this is the concept of absolute. Okay, so here this is glass, this is water. We are talking about absolute. Now put this information back here, and you see that this quantity actually becomes 9 by 4 divided by 2. So that is 9 by 8, which by the way is also equal to, it can also be expressed in terms of absolute refractive index. So it is absolute refractive index of glass divided by absolute refractive index of water. So that is why in terms of formula, this becomes like this, that refractive index of medium A with respect to medium B is absolute refractive index of medium A with respect to free space divided by absolute refractive index of medium B. But that also in fact becomes what? It becomes this thing, C by VA divided by C by VB. So in terms of velocity, it is the inverse of the ratios. It is velocity of light in B divided by velocity of light in B. But for now, for us, this will be the more important. So that is about refractive index. And as you know from a long time, refractive index is a dimensionless physical quantity because it's defined as the ratio. So quickly, about a quick refresher about the definition of refractive index. And you can think of refractive index like a physical property of a medium which can be determined experimentally. There is a way to determine it theoretically also from the two properties. One is the electrostatic property of the medium called the permittivity of that medium, or the dielectric constant of that medium. And the other is the equivalent property in magnetism to do with magnetic field, where it is called relative permeability. So just like you have dielectric constant K, so it makes the permittivity of the medium from epsilon naught into K epsilon naught. Like that in magnetism, you have permeability mu naught, and for a medium which has relative permeability, the permeability becomes some factor into that. So you will later learn in Maxwell's laws and electromagnetic rays that the value of mu actually can also be theoretically determined from the two constants. One is the dielectric constant and the other is the magnetic permeability constant. Okay, but at the moment you just think of it like this is experimentally determined. So we know for water it is typically about 4/3. For typical glass it is 3/2. But of course there are many different grades of glass which have different values and all that. Okay. So that and all is about this. Okay, now let us come to Snell's law. So hope this is clear so far. Now Snell's law tells us, which is an experimentally determined fact, that when a ray of light experiences an interface of a denser and a rarer medium, so let us say this has a refractive index mu, and here of course we have air. Let's take that as the first case. So imagine we have at a particular point we have an incidence. So I'm drawing the normal first. So we have a ray of light, let us imagine, which is incident from air to a point which is on the interface. There's a plane interface of a denser medium. Okay. So this thing over here is the denser medium, okay, and this is the plane interface of air and the medium, whatever that medium is, glass or whatever. So Snell's law is an experimental law which tells us that this particular ray of light going into a denser medium, it will bend towards the normal. So it will bend in such a way that this happens. It will deviate from its path in such a way that if this was the angle of incidence, now the angle of refraction will become less, and become less given by the formula that in this case the formula will become sine of I is equal to the refractive index of that medium into sine of R, where I is called the angle of incidence. And R is called the angle of refraction. Because this particular ray here now is called the refracted ray. Or sometimes we also call it the transmitted ray, whereas this is the incident ray. So the incident ray bends towards the normal when it goes into a denser medium. Now if you just apply the principle of reversibility here, you will understand that when it is going from a denser to a rarer medium, okay, when something like that is happening. So now let us say we got glass over here which has refractive index mu, and we've got air on this side. Now when there's an incident ray which is making the journey the different way, it is coming from glass, incident at a point like this, such that if we drop the normal, so this is my angle of incidence. So now what will happen? It will bend away from the normal because it is going into a denser medium. And this you can just think of that I'm applying reversibility to that previous diagram. Just think of it that way. So here R will become greater than I, because here the principle will now become is the same pair of R and I, but here it will become sine R is equal to mu sine I. So this diagram that I've drawn here and the previous diagram that I've drawn there are basically the same thing, but just with reversibility. Just imagine the angles are all the same. So now I'm reversing the role played by the incident ray. The reflected ray over there is now becoming the incident ray over here, and the incident ray over there is becoming the refracted ray over there. or the transmitted ray. So this is okay. Now, when we extend this principle to general media, instead of air and a denser medium, it becomes like this: that if we have the interface between one medium which has refractive index mu e, like let's say this is water, and another medium below it which is having refractive index mu b, which is let's say glass, and this is the plane surface. Okay. So this is not like a glass plate and air below. This is a solid chunk of glass. You've got a solid chunk of glass like this, and above that you have a layer of water. So here what will happen is, if there is any incidence at any point, it will always tend to be in such a way that if the ray of light is going from denser to rarer, then it will bend away from the normal. And if it is going from rarer to denser, it will tend to bend towards the normal. And that will automatically show up in terms of the formula. Okay, so the formula in that sense is universal. Okay, so if we have something going from glass, which is denser, into water, which is rarer, it will bend away from the normal. So this. Because on the other hand, if the same thing is happening in reverse, if this is the incident ray, this will become the refracted. So if I take the angle, this one as theta e, and if I take this angle as theta b, so the general formula will become mu a sine theta a is equal to mu b sine of theta b. Okay. And this applies to both the cases. In one case, as you can see, I'm going from glass to water. So in that example, theta b is the incident angle and theta a is the refracted angle. And what is happening? The ray is bending away from the normal, because water is rarer. The refractive index of water, which I have taken as mu a, is less than the refractive index of glass, which I have taken as mu. So this formula is showing you this. But in the other case, if I am going from water to glass, where I have reversed my rays, then it's just the reverse. Theta E is the angle of incidence and theta B is the angle of refraction. So it is bending towards the normal, because it is going into glass from water. So glass is denser. So glass being denser, this is what is happening. So this is the general statement of Snell's law that we always use now, that mu a sine theta is equal to mu b sine theta b, or mu 1 sine theta 1 is equal to mu 2 sine theta 2, irrespective of what is the incident ray and what is the reflected ray, because it's just a case of, you can apply reversibility. So in whichever case you're talking about, you can take accordingly. Why it bends, Ganesh, is very interesting. It bends because the speed of light changes. And there is no way to geometrically understand that. The only way to understand that is from the wave nature of light, which you will understand by something called Huygens principle. So I'm just keeping that discussion for another day. But if you like, you can. Huygens principle is something you can go through yourself from H.C. Verma. It's there in the first section of wave optics, or you can even go through it from Resnick-Hallett. It's very interesting. So Huygens principle not only explains things like diffraction and interference and all that. The first thing you do with Huygens principle is that you understand the laws of reflection and refraction. You actually sit and prove it. Okay. And there is another very interesting proof also, but that comes from something else altogether, which again I will talk to on the day when we do doubts. It comes from something called Fermat's principle in light. That light always takes the shortest possible path from one point to another. So you can also prove the Snell's law as well as the law of reflection by using differentiation and maxima minima, and by just using the trying to visualize that if light is going from one point in one medium to another point in another medium, what kind of path it should take so that it will reach in minimum time. What we mean by shortest path is actually minimum time, or something called shortest optical path length, which again we'll come to later. So that Fermat's theorem is actually not part of your syllabus, but your calculus is advanced enough at this level to be able to understand the law of refraction from that. So that's another interesting thing we'll see later. Okay. But currently, let's move on to two very important formulae related to this, which you will be using in various types of questions. Okay. The real depth apparent depth formula and the slab formula. Okay. So next, let us see from refraction at a plane surface. You people have a lecture at 6 o'clock, is it? Or okay. So I will just take about 10 minutes. Okay, I will leave you in by 5:40. Okay. So this is something very simple. Okay. So you have a plane surface like this, and let's say you have water, which has refractive index 1.33, and on the other side we have air. Now what is happening is you have a point object somewhere here, which is at a certain depth. So this depth I'm showing as the actual depth. So I'm writing that as D, capital D. Okay. And you interestingly have an observer who's for whatever reason hovering right on top of this. So he is seeing what we call the normal view of this. So he is seeing. Any other way. So his line of vision is perpendicular. So that is the assumption I'm making. That is line of vision for this object is perpendicular. But as you all know, his depth perception goes wrong because of refraction. He doesn't perceive it to be at the actual depth D. He perceives it at a lower depth. Okay. So now what I'm going to do is I'm going to show you two rays, but you will have to imagine that they are very close to each other. So one is the ray which is actually along the principal axis, along the normal direction. So this ray is the actual ray. So this is making an angle of incidence which is 0. Okay, so it will go undeviated. As you can see from the Snell's law formula, mu1 sin theta 1 is equal to mu2 sin theta 2. So if angle is 0, then this angle here will also be 0. So this is fine. Now the second ray is the one where you will have to imagine that my diagram is actually much more intricate than it is, because you'll have to imagine that this angle is very small, so that this ray is actually close enough for him to receive it. You can see in my diagram, these two rays are very divergent, so there's no way the eyeball of this person is going to receive it. But just imagine that this angle which I've drawn here, this angle alpha, is actually a very small angle. So imagine alpha is a small angle like half a degree or something like that. So this ray, let's say this point is Q. So this ray OQ, okay, this is actually a paraxial ray. So the derivation we are doing here, about to do, it is to do with what we call normal vision. So that is when you are viewing, okay, viewing light coming out of a plane surface, but along the normal direction. Now you might say, if I'm viewing along the normal direction, why am I affected by refraction? The answer to that is there's only one unique ray which is actually perfectly normal, and you will never get the image from just one ray alone. There have to be multiple rays that your eye is receiving, and your eye is reconstructing the image on the basis of that multiple rays. So your eye will actually be receiving, even when you are viewing normally, it will be receiving rays which are normal and very nearly normal. So in other words, it will be receiving the paraxial rays. Okay. So now let me magnify this diagram a little bit and explain further. So what is happening here is, now imagine that these two rays are very close, the PQ1 and the normal one, the OQ1 and the normal one. So what is happening is your eye is reconstructing the image based on this refracted ray which has come out undeviated, and this refracted ray which has come out with deviation. So your eye actually gets fooled into thinking that this ray is coming from somewhere here. So this point becomes like the virtual image of that point object O. So that is why your depth perception goes wrong. That is why now you perceive that the depth of this object is only this value D prime instead of D. Okay, so hope this point is clear. Okay. Now let me come to the law of refraction over here. So how we'll apply law of refraction is, at the point of incidence over here Q, I'm drawing a normal. So this angle is my angle of incidence, and you realize it's the same as this angle alpha. Is this angle alpha, and this angle is my angle of refraction. Let me denote it as beta, and you realize that is the same angle as this one, because this refracted ray only I produce back. That is this dotted line which is meeting the principal axis at this point I. So this angle is the same as this angle, which is beta. Okay. So now next thing I'll do is I'll apply Snell's law over here. So zooming out of the diagram again, I will apply Snell's law. So remember, we are going from water, which has refractive index air, to refractive index mu, to air, which has refractive index equal to 1. Okay. This is mu air, this is mu, sorry, not glass, water, whatever. So what is my Snell's law telling me? That mu1, that is refractive index of water, times sine theta 1, which is nothing but sine alpha in this case, is equal to mu of the other medium, which is air, times sine theta 2, which is beta. So it just so happens that over here 4 by 3 times sine alpha is equal to 1 into sine beta. So this is my Snell's law. Okay. Now add the fact that alpha is a small angle. So supply or factor that in over here. So you can say that sine alpha tends to alpha. So we get 4 by 3 alpha tends to beta. Okay. And now come back to this diagram, and you see that if these angles are small, these right angle triangles, that is, if I label this point over here as, let us say, N or something, then the right angle triangle ONQ and the right angle triangle INQ, they actually have very small angles. So we can apply the tan alpha tending to alpha formula for those triangles. Okay. So for triangle ONQ and triangle INQ, we have tan alpha equal to NQ, that is perpendicular, upon base, which is nothing but ON, which we will see is the real depth. And for that one, we have tan beta equal to NQ divided by IN, which is the apparent depth. So factor in these two formulas. Second formula here and third formula here. Whereas we've already got the ratio of alpha and beta as mu from the first formula, which is coming from Snell's law. So now factor in all this. So you can see that beta, or let's say alpha upon beta, alpha divided by beta is equal to 3 by 4, or better written, this is 1 upon refractive index of water with respect to air, because it's 1 by 4 by 3. Okay. And this can be approximated as tan alpha by tan beta. So that is 1 upon refractive index of water with respect to air. And further, tan alpha and tan beta are nothing but tan alpha is NQ divided by the real depth D, which is ON. And tan beta is similarly NQ divided by the apparent depth, which is D prime. Okay. And that is equal to 1 upon refractive index of water with respect to air. So the general formula that we get now is that the apparent depth D prime is equal to the real depth D divided by refractive index of water with respect to air. Okay. So this is the formula that I gained quite a few of you as a hint also for some of the HC Verma problems. Okay. And this formula corresponds to this diagram. And this is all that you will require in all the problems where there is refraction at plane surface. And there are quite a few problems like that. So that is why, for example, practically in this case, what will happen is that the apparent depth will appear to be 3/4 the real depth. So approximately every time you look straight into water, an object lying at the bottom of the pool, like a coin at the floor of a swimming pool or something, it appears to be at only 3/4 the actual depth. Okay. But what I want to bring to your attention here as we just conclude is the nature of this formula and how it is general. It is not only when you're looking into a denser medium. You could be looking from a denser medium into a rarer medium, and the formula will still apply, but in reverse. Okay. So that is why how we should remember the formula is in the general form. you should remember the formula in this form, that if we are looking at the interface between medium 2 and medium 1, and our object is present in medium 2 and our observer is present in medium 1, then to the observer the object will appear to be like this if mu2 is greater than mu1, and the apparent depth will be given by the formula d divided by mu of 2 with respect to 1. Okay. Whereas in the same case, if on the other hand, so this is the case, the ray diagram that you've already understood. Okay. But if on the other hand I have a situation where this is mu2 and this is mu1. Now suppose mu2 is less than mu1. Like for example, suppose this is glass and there is a layer of water below. This is water. So that kind of example. Okay. And your observer is watching from the other side of glass. Or let's say your observer is somehow embedded in the glass, so it doesn't really matter. But he's looking into water. So your object is like this. So this time you will see what will happen to the rays which are coming out like this. These rays will actually bend towards the normal because they are going into a rarer medium, into a denser medium. So they will tend to bend towards the normal. So when your observer produces them back, they will tend to meet the principal axis at a lower point. Okay. So they will tend to meet the principal axis at a lower point over here. So again, your apparent depth will be given by the same formula. It is real depth upon refractive index of 2 with respect to 1. But as you can see, this will become d into mu1 by mu2. And this time what is happening? Mu1 is greater than mu2. So your apparent depth will become greater than real depth. So this is the thing in its generality, that when the light is going from mu2 to mu1, the light that is coming out, it is going from mu2 to mu1. Then the formula for apparent depth is real depth divided by refractive index of 2 with respect to 1. Now it is just two cases. If mu2 happens to be greater than mu1, then d prime will happen to be less. If mu2 is greater than mu1, then your apparent depth will be less than real depth. Whereas on the other hand, if mu2 is less than mu1, then your apparent depth will become greater than your real depth. Okay. So this is the thing you have to remember, that this thing automatically comes from this formula and what we substitute for mu2 and mu1. Alright, so this is going to be important as you are going to apply refraction at a plane surface in various problems. Okay. So, just as a practical example of this, I will tell you. Okay. Quick thing before we conclude. Okay. Suppose we have a situation like this where this is the surface of water in a pool or something. And I have one object E, like one swimmer or somebody, who's at a depth of, let us say, 12 meters. Okay. And I have another object B, like somebody flying above or a drone or something, who's at this height in air of, let us say, whatever, 18 meters. Refractive index of air is 1, refractive index of water is 4/3. Now you want to understand the position S of E as seen by B and the position of B as seen by E. Had there been no medium in between, both the answers would have been how much? Both the answers would have been 18 plus 12. You understand the point? But here, because there is refraction involved, one will be greater than 30 and one will be less than 30. Okay. So I want you to quickly apply this and tell me what will happen. Which one will be greater, which one will be less. So B looking at A, the refraction is happening from water to air. Now, so the index of refraction you will substitute in the formula will be what? Refractive index of water with respect to air. So you will see your apparent depth will become less than your real depth. Whereas the other one, A looking at B, the refraction is happening from where to where? It's happening from air to water. Yes, Ganesh, I think your answer is correct. Okay. So here if you see B looking at E. Okay. So A is the object. So the refraction is from water to air. So the apparent depth of A, B prime of A below the water surface will be the real depth of A below the water surface divided by refractive index of water with respect to A. So it should be 12 meters divided by 4 by 3. So it should be how much? It should be 9 meters. Okay. So then the position of this thing A as seen by B will just be, it's the water surface is 16 meters below. Was it 16? Sorry, it was 18. So 18 plus 9. Okay. The surface is 18 meters below, and then the apparent depth is appearing to be 9. So if you can see it is 27 meters below. So to B, A's position will appear. So B will see A at a position of 27 meters below. So this becomes the application of the formula, right? Whereas when I see the other thing, A looking at B, so the rays coming from A, from B, as they hit the water, they will bend towards the normal. They will bend towards the normal. So when you produce these rays back, they're giving an image of B somewhere here. So the apparent height of B above A will become more. Okay, so that is the concept. So B as seen by A. So for this, the refraction is from air to water. Okay, so B is the object. Okay. So the apparent height of B above will be the real height of B divided by refractive index of air with respect to water. So that will become 18 divided by 3 by 4. That will become 24 meters. Okay. So the apparent height above the water level for B will be 24 meters. So the position of B as seen by A will be this apparent height of 24 meters plus the actual height of the water level above, which was whatever 12. So it will become 36 meters. Okay. So hope the calculation and the rough ray diagram that I've given above is also clear to all of you. So this is a very critical thing in application of refraction now. Up to 9/10 you have studied apparent depth is always less than real depth and that kind of thing. But when the light is going from a rarer medium to a denser medium, the other thing happens, the opposite thing happens. So the depth perception goes the other way around. Something appears to be deeper. So from underwater, you're looking at air above. The depth of something in air will appear to be more than its actual depth. Whereas from air, you're looking into water, the depth perception will be on the other side. It will be less than what it is. All right, people. So with that, we conclude today's lecture, and I'm going to send you some assignment and reading work also for this. Okay. Plus continuation of problems from HCV. All right. So